Because what we're going to get into here in a little bit is if you're really going to fly crew very safely with an extremely reliable system, it has to be designed to do that. So we're starting with a system designed to what we believe is the most driving case. And then when we fly cargo and satellites, if we tend to want to take out some of the redundancy on the system, take some of the systems out, we will do that. But anyway, we start off with the launch. The launch abort system comes off during second stage. We don't want to carry that extra weight any further than we have to. So it really is just flying for about 3 minutes before it comes off. The second stage burn, roughly ending around 9 to 10 minutes. And now our space vehicle is in orbit. So from that point on with the service module, which is very capable. And I mentioned earlier that I don't need all the capability of the original design that Lockheed and NASA have been working on. However, I do have that as an option. If one of my options is that, as an example, space station needs reboost capability, I can carry more propellant and bring that to the station. Or instead of carrying those tanks, I can bring external cargo unpressurized. Our system is designed to remain docked to space station per NASA's requirements, which is over 6 months, 210 days, and then use the service module to deorbit it, come back home. Our baseline is a water landing. And you say, why water? And the real fact is you have to be able to go into the water regardless. When you're launching from Florida, the abort scenarios are such that, hey, if you have to abort, you will land into the water, and so you have to be designed to land in the water. We have been designed to land in the water from the very start, to including some parachute tests that have already gone on. You'll see pictures where there has been water testing as well with the capsule, just to look at buoyancy, uprighting, the different systems. We are also carrying the trade of land. Contingency reasons, we can land on land. So if for some reason the crew winds up landing on land, the crew will be fine. My reusable spacecraft probably won't be so fine. And so we are evaluating trades to see if we want to also have land landings for the reusable spacecraft. Along the bottom here, if you look at this, about when you want to start doing all the mission operations, the planning, working with the range, you have to start early. As a matter of fact, last week I briefed General Cotton at the 45th Space Wing, who controls the range, and so the flight termination systems are very critical. We feel we've got a head start on that. We've been working very closely with L3 for the FTS, as well as other integrated avionics. And I know from previous experiences, if you don't start that early, you're late. We are. But you may notice here we say crew training T-minus 3 to 6 months. And T-minus 3 months may sound short. That's our intent. Our intent is to make this system very user-friendly, require as minimal training as possible. And the truth is, the reason it says 3 to 6 months, it depends on the crew, and it depends somewhat on what NASA wants, how thoroughly trained they want their astronauts. And if we're flying tourists on other missions, that training flow will be at the 3-month end of it. If you look at our takeaway banner down here, we say that, hey, we leverage the safest systems ever developed. And we are going to get into that because that is actually one of our values. Here's a photo of our composite crew module. This was the test article built back in 2009. Today, as we speak, and there may be some composite module experts in the crowd, it's undergoing permeability testing at the Marshall Space Flight Test Center. One of the issues or concerns when the composite module was built was composites are permeable. So they don't hold air as tightly as, say, aluminum, lithium, or a metal. And so will it meet the requirements, particularly for a beyond low Earth orbit, if you're going on a deep space mission? Will it meet those requirements, or will you have to carry extra air for pressurization? So it's undergoing that testing. Initial results come back and say, for a space station mission, it looks like we meet the requirements. We are also, I say we, but NASA Langley leading this, is evaluating liners that you actually kind of paint on like a paint which are of a sealant, to make it even less permeable. We're going through those evaluations, but it's good news that for station we already meet those kinds of requirements. The picture next to it is, this is a pressure shell that was designed as an alternate for this outer mold line. Our outer mold line is going to look just like this. So the heat shield won't be as thick because it doesn't need to be coming out of low Earth orbit as it does coming back in from a lunar mission, for example. But when you stand back and look, we are leveraging all the engineering, all the development, all of the testing, and the infrastructure that has gone into this system around our composite pressure shell. And so not only the mold line, but also with Scott sitting here from Lockheed, Lockheed's got probably the leading rendezvous docking simulation center in the world in Denver, Colorado, that we have access to for practicing rendezvous and docking with station. They also have a couple of different mock-ups of different fidelities between Houston and Denver, so we can use it for cockpit evaluation and crew ingress, egress, all these things that you have to think about as the total service provider. We've got a head start on because we're leveraging a lot of work that NASA and Lockheed have been doing for the past 6 years. Here you can see a drop test going into the water of our mold line and system. And then lastly, the service module. Interestingly, the service module lead design on this is out of NASA Glenn Research Center. We've taken that and reducing it in size and capabilities I spoke about earlier, but very capable to do everything we need to get our capsule to and from the space station safely. Launch abort system. You know, this is a system that you can't underestimate the complexity or how difficult it is to design, test, validate, and be comfortable with. But like an ejection seat in fighter airplanes, when you think you need it, or in our case as well, when our computers think you need it, it's got to work. And so to be that confident in it, you have to start early. Once again, we've got one test flight under our belts, and I say we, NASA Wallops did this testing to look at the aerodynamic properties. At ATK, this ogive, so this sits over the capsule. This ogive is going to be composite, and our composite buddies sitting over here are happy with that. It's got 6 of our solid rocket motors on it to propel it, and we have designed it to be very capable. First of all, it's got to pull the capsule off of a first stage that's still burning and outrun it. It easily does that. One of the real driving cases that it's designed to meet is a pad abort. So if there's a fire on the pad and the crew and the capsule need to get away from it, you want to make sure you get well away from it in a mile. You basically want to wind up a mile away from the pad so you don't wind up anywhere near the fireball or the explosion if there is one. And our system does do that for us. Here's, earlier on, I kept saying our system is the safest ever designed. And I'm trying to, in these next couple of slides, show you why I believe that's true. And matter of fact, if there's any questions, I would love to answer them as we're going through this. But this one is really trying to tell you that if you're going to design a system to be very reliable and ultimately safe, in the rocket world, you look at where we've had failures in the past. Where are the opportunities for you to wind up with a catastrophe? You want to avoid, you want to reduce those number of opportunities, if you will. And I know I'm calling opportunities, but if you look at a stage and the reliability of it, it's probably a fair number to pick 99.5%. So in this case, I'm circling the second stage. 99.5% of the time, that stage will work without resulting in a catastrophe. But what that means is 0.5% of the time, it will result in a catastrophe. And so you want to minimize those numbers. Unlike in aviation, and by the way, I flew the F-14, I was really happy to have 2 engines, because if I lost one, The second one, I could complete my mission and at least get the airplane back safely, or at a minimum, I had an ejection seat so I could wind up back on the Earth safely. In the rocket world, that's not the case. That an additional engine now is just an opportunity for a catastrophe. If you have two engines and you lose one, your mission's over, so you're in your ejection seat already. So you really want to minimize any complexity. You want to keep it very, very simple. And so with Liberty, we have one first stage engine, one second stage engine, and then my third stage here, my abort system. And if you're reading the words on top, I'm saying, hey, the abort system, I'll give it a 90% effectiveness, which is maybe a little kind. You know, we're figuring on Liberty, our abort system, which we believe is the best one. We think 85% is probably a good number to give it. But to make the math simple, if you have a system like this, with each stage 99.5% reliable, the combination of the two means you have a 1 in 100 system or a 0.99 system. But if out of that 1 in 100 times that it fails, if 9 out of 10 times you save the crew because of your abort system, now your system ultimately means, hey, the crew will survive ascent 1 in 1,000 times. That is an order of magnitude better than when astronauts climbed on the space shuttle in the U.S. And this is not an accident. This was how it was designed. And just to kind of put it in perspective, if your system had 3 engines on first stage, 1 on second stage, you wind up with about a third of the reliability, with every stage being the same reliability. And I have put in a complexity factor of 0.99, which means if you take a first stage and now you make it more complex where the pieces interact, and the space shuttle is a perfect example of this, and I'll get into it a little bit more later, but if you have interactions, in this case of the space shuttle, we have a side-mounted shuttle on an external tank with 2 solids strapped onto it. Those interactions are, in fact, what led to losing both Challenger and Columbia. The interactions, when you make a system complex, your reliability goes way down. So you want to keep it very simple. So this is shown, hey, not only is Liberty simple, as we can see here, but it's based on heritage systems. Business case, that really helps me. For the overall safety and reliability of the system, that really helps me. We're leveraging all the work from the space shuttle boosters, 220 booster flights without any major flaw. We're leveraging the Ariane 5 system, which has flown 47 times and counting as our second stage. And then on top, we have our composite crew module designed to meet NASA's human ratings, all those requirements. And by the way, sometimes you read where, hey, NASA's requirements, by the way, which 1 in 1,000 on ascent was NASA's original requirement. It's now 1 in 500 for the combination of ascent and entry, which really kind of means the same thing. We absolutely meet those requirements. We exceed those requirements. There's another piece to the story. And again, this feeds into why I'm saying Liberty is the absolutely safest vehicle. And that's the trajectory. So if you design a rocket to lift payloads, an expendable rocket, and by the way, a lot of my team, in fact, did that from the Titan days to the early Atlas days, you design it for that mission. And you design it probably with a trajectory that is lofted, that goes up. And the reason you do that is you're interested in getting the most payload to orbit, so you minimize weight on your stack wherever you can. So if you can have a smaller engine and get away with a lower thrust to weight, you do. If you can have thinner tank walls because you don't have to stay in the atmosphere as long and the dynamic pressure or the Q are lower, that's what you do. If you're putting a human on there, if you're on this trajectory, anywhere it's red, if that second engine quits, even with an abort system, the crew dies. which sounds, hey, wait a minute. I don't understand that. I don't believe that. If we look at my chart here, and if I were to say, hey, the atmosphere level is kind of where my laser pointer is down here, if you're flying humans, you want to stay low. You want to stay close to the atmosphere. You need a thrust weight on your rocket that allows you to do that. You need a trajectory that stays in the atmosphere, but it's depressed in angle. Rather than going straight up and getting out of the atmosphere, you actually want to stay in the atmosphere. You want a dynamic pressure that's higher, and so on Liberty, we're up over 600 PSF, which may sound high, and fighters we're way over that. We're way multiples over that all the time. You just have to design your system to withstand those kind of loads. Because if and when your propulsion stops working for you, you need your capsule to be on a trajectory that the crew can survive. So if you fail on this red curve, the pull-out forces are so high that the human body can't survive that. So Liberty is absolutely designed on a trajectory with the thrust weights out of both our stages to allow us to do that. And we have no black zones, is how we've come to call them. Anywhere through our trajectory, you can lose total propulsion and the crew is safe. It's a trajectory that supports the crew living. I believe we're the only rocket design that does this. The other thing, so we've talked about keep the system simple and reliable. Design it to carry humans, because that's a very, very different mission. And then thirdly, though, hey, we need a team. We need to make sure we have learned from the past. And I talked about interactions. And matter of fact, I've got the 2 patches up here from Challenger and Columbia, which, really can be uncomfortable to talk about. I was involved in launching Columbia in my previous role as the head of the astronaut office. So I've thought about this a lot. And the fact is, when you look at Challenger, that was the 25th flight of the space shuttle, particularly early in programs as well with new equipment and hardware, you learn things. Sadly, we learned one the hard way on Challenger, but our solid rocket booster, the joint was not as robust as it needed to be. So particularly if you flew it in cold weather, the joint leaked. The joint severed the strut that attached it to the rest of the stack, and it immediately turned into a fireball, and a very bad day for all of us Americans, especially that crew. In fact, that joint, if that motor had been on Liberty, that leak we probably wouldn't have even known about until we recovered the first stage. And that's kind of back to the point of my interactions. You want a system that's simple. So the joint in itself leaking started the problem, but had it not been pointed at a strut that it cut like a blowtorch, we would have gotten by that day. If you look at Columbia, the same thing. It was the interactions of the system. That big liquid fuel tank shed foam. It hit the leading edge of Columbia. We didn't realize that Columbia was damaged like it was. We knew foam had hit it, but the fact is our analysis came back saying, hey, we were fine. Obviously, that was the wrong call. But the interaction of that system now resulted in a vehicle that didn't make it back in the atmosphere and us not knowing it before it was too late. So we need to learn from this. And the fact is, being with ATK and solid rocket, sometimes folks go, hey, well, solid rocket motors, I think a Challenger. And I like to say, absolutely, that's fair. Challenger was the 25th flight of the shuttle. After that, we flew the shuttle 110 times, and that redesigned system now is arguably the safest one that's ever flown. So we've learned from that. We need to continue to leverage that. I've got a chart down here, one that just talks about probabilities. When you climb on an airliner, I don't really know what your chances are, but they're 1 in millions of you having a very bad day. When I flew in Desert Storm in my Tomcat, so when I was up over Iraq during the war, my chances of being killed on that flight were 1 in 20,000. When I climbed on the space shuttle, my chances of being killed on ascent were, and this may be a little nice, but 1 in 200. You know, now in the 21st century, we can absolutely do better on that. And in Liberty, I believe we can exceed 1 in 1,200 on ascent, given how this system has been designed. One other benefit of solids, if you look at expendable program, the Delta program for the Air Force with strap-on solids, and you look at the Space Shuttle program, obviously with strap-on solids, and you look at what's driven launch delays. In the Space Shuttle world, weather was the biggest. The liquid system came in next at 20% of the delays. But the solids, only 2% of the time did the solids result in a delay. So they do bring with them the fact that they have been proven to be very available. They result in very good launch availability. And it turns out, same, less than 2% of the time in the expendable world as well. So at this point, thank you for my indulgence. I want to hand off to John Shoemaker for the second half of the briefing and give us the insights into the top half.
You hit the left over there?
No, it's actually hitting the right arrow.
Oh, cool. Okay, thanks. Thanks, Ken. And thanks for the opportunity to join in the presentation here today. Like was mentioned earlier, I head up Astrium's activities in the U.S., and that's part of EADS North America. So we have an American team and a European team. Astrium is Europe's largest space company, and what it brings to the table is it produces the Ariane 5 launch vehicle, which has flown 47 successful consecutive times. 3 of those missions in the last 4 years have been taken the autonomous transfer vehicle, a pressurized cargo vehicle, to the International Space Station. The Astrium folks also build the ATV. So you have a very experienced team that is used to the rigor of station ops, both launch and operations with the space station. In addition, Ariane 5 is the world's most successful commercial launch vehicle, tremendous record on the commercial side of the equation, and brings that to the business equation. Our team is very excited about being part of what we think is a top world-class commercial team that's going to bring commercial crew and can bring cargo to the U.S. for launch. Ken's covered a lot of the pieces already, and I'll reiterate a number of those. What we're going to talk about here first is the Liberty upper stage, which is, as he showed you on a diagram before, it's actually the first stage of the Ariane 5 launch vehicle. So we bring that stage in as the second stage for Liberty. It'll require some modifications. The structure will need to be strengthened a bit because it's now the second stage. And obviously it has to air start since it's the second stage, and both those developments are in work with the team. I should also mention that, and Ken's very subtle about it, but the Liberty team, the way ATK has done a beautiful job of bringing it together very fast, worked through a lot of issues with both ATK and Astrium at the start and the onset, and now bringing together the other teammates, bringing on Lockheed Martin. It's a tremendous team with a lot of proven experience to bring forward a very lean commercial product. What you see here is the stage, what will be the Liberty upper stage, and it is powered by the Vulcan 2 engine, which is provided by Safran Snecma. Again, that engine, as part of the Ariane 5 first stage, has launched 87 consecutive successful times. The chart here, this is ATK data, and what it shows, this is another one of the issues you've heard about in the past, I'm sure, thrust oscillation. Well, what happens with when you take our first stage and put it on as the second stage, compared to Ares 1, the tanks are actually flipped. You have the liquid oxygen tank on top, liquid hydrogen on the bottom, and when you then look at the complete stack, and this is ATK data, the blue is, as it shows, when you really take a conservative approach and look at all the issues set with thrust oscillation and how that could harmonize with that stack, and then compared, the lime green in the middle is Liberty, and you can see it basically becomes a very, very almost de minimis issue with the Liberty stack with our upper stage. Okay, now again, Liberty is it's a transportation service, right? And it's a transportation system. So what this shows you here is how the component parts move through the system, and as Ken said, go through a very fast, lean process to get to launch. Up top, you have the space vehicle, the MLAS, the capsule, and the service module come together. As you see, they work through and come to the VAB. Likewise, the 5-segment solid is transported from Utah, comes to the Cape, and comes to the VAB to get integrated. And at the same time, you can see the ship in the middle, which actually brings the stage from Europe. It's a shorter trip than it goes now to Kourou, to French Guiana for launch down there, again for assembly in the VAB. I should also add what our plans call for is initially the development work and the stage are built in Europe. As our business plan matures and we get traction in the U.S. market, the understanding and our thought process is to look to bringing that work to the United States. So all comes to the VAB, the stack is assembled there. There's integrated testing through the LCC, and you see the continuing emphasis on wise use of existing infrastructure now in a commercial setting. So LCC for integrated test, then out to the pad for launch from LC39. This all sounds very simple, but this is where all this proven experience of ATK, Lockheed, Astrium in the launch operations on orbit, rendezvous and docking. Ken touched on the capabilities Lockheed can bring to bear with that human-rated capsule. Likewise, what Astrium brings is the experience with the autonomous transfer vehicle of the rendezvous and docking with space station and all the rigor of getting that, the ops on orbit, and then the whole operation with the space station partnership team. Anyway, so we launch. We have our mission ops through Houston, recovery and refurb, like Kent had said earlier, water landing, land landing being contemplated, and actually the reusability is looking at 10 flights for reuse with water landings. And again, the catchphrase at the bottom is key: optimizes use of existing people, a great experienced team in the U.S. and certainly with my colleagues in Europe in these human-rated activities, processes, and infrastructure. Okay. The commercial approach. Can't emphasize this enough because here are some very seasoned companies, some very proven teams, taking a very hard scrub at the way they operate, the way they do business, and looking at a very lean commercial approach to come at the Liberty system. I'll tell you, one of the benefits of this U.S.-European team is the experience with Ariane and that Astrium has in commercial launch. For example, as we were working through the Liberty system, the launch vehicle itself can launch any spacecraft that's considered by NASA for human rating and launch to space station. It's got that kind of capacity, and Kent mentioned earlier, it has that capacity and then some for the lift of bringing things to orbit. So very versatile, and the business plan contemplates being very flexible in what is brought into low Earth orbit. Again, if you look at what we're talking about here, and this is just what Astrium brings to the table in ATK. If I start at the bottom piece, Ariane 5 has the lowest insurance rates in the industry because of that success and consecutive launch rate. Again, I'll wear it out, but 47 successful consecutive launches and for some very demanding commercial customers. The look that we've been doing, that ATK's been doing, that Lockheed's been doing, is reevaluating processes and getting very lean to yield a continually scrubbed commercial product. For example, as we work through the upper stage for Liberty, the work that literally would have taken hundreds and hundreds of people before, now because of the seasoned Ariane 5 team, is being done by dozens of people as we do the development work for this new upper stage for Liberty. If we turn to ATK's side, again, several decades of manufacturing, integrating, and launching rockets, and the list of the rockets is there. And On the side here, you see, of course, Ariane 5, and then you see several ATK products with composite cases, use of solids, and in very innovative ways from providing a booster to providing a whole stack, if you will. And add to that the capabilities Lockheed Martin brings to bear in the whole launch structure and their high pedigree with fielding the system, the mission, the ops. It's tremendous. Okay, if you talk about our business case, what kind of missions are we talking about? Well, certainly ISS crew, and we're in the competition for the NASA Commercial Crew Integrated Capability, and very proud of the offering we've brought to bear on that. The U.S. government satellite market, DoD, NASA, NOAA, we think this capacity has tremendous potential there. NASA cargo up and down, certainly with a capacity like Liberty, you can bring crew and cargo because of the performance of the vehicle. You can also have a pressurized and unpressurized cargo volume. Space tourism is certainly in the offing. This is a very interesting one. The idea here, and ATK has led to discussions with several nations about a shuttle space lab type, if you will. Liberty with crew, with cargo, can give another nation, a private sector company, the ability to go up and run its whole own test program and have that experience that it puts together, formulates, and executes through this commercial offering. And the cost benefits, we've talked about a lot, but existing manufacturing, a great proven team that can bring this to bear, short development time, and can't emphasize that enough, and I think you saw that throughout the chart, across the whole service. Mature components, proven systems, existing infrastructure, and synergistic with other programs. Okay, so we're not shy about saying we think Liberty, the service, the system, brings an unprecedented capability for crew, for cargo, for government satellite launches to the United States. It can deliver more crew and cargo mass volume to ISS than any other provider. Benefits from the extensive use of lessons learned to minimize cost, technical risk, programmatic risk, a strong sustainable business case with ISS, but beyond that. And we think it's the start of a sustainable U.S. commercial launch capability to LEO for generations to come. And as Kent has said several times earlier, we believe Liberty provides the safest, most reliable access for commercial space. Okay, this is a short video that shows with our team talking about why we are building Liberty. If you could roll that, please. What's it? Oh, it's just.
You know, we didn't get the
just
whole...
hit this. That's the next slide.
It looks like we're not getting the whole slide.
Which way? Sure, please.
Yeah. Just click on that.
Oh, on the slide itself. Cool.
It's harder to run than a VCR.
My fondest dream is becoming an astronaut.
NASA has the most capable astronaut corps in the world. They are deserving of the most capable spacecraft in the world. That vehicle is Liberty.
I will see space and planets. I will hear the countdown clock. I will taste astronaut food on a mission. I will touch the controls. I will smell space. Inside I will feel happy and excited. I wrote this poem.
By offering Liberty in a commercial environment, it allows us to bring additional commercial practices and streamline activities to the Liberty program and also other launch programs as well.
The Liberty approach to mission operations is to provide streamlined processes to ensure a cost-effective commercial approach.
The Liberty ground system supports the Liberty business case by reusing the facilities and the ground support hardware at Kennedy Space Center.
I was responsible for assigning over 25 crews to the Space Shuttle and the International Space Station. I would be extremely confident to assign America's future astronauts to fly on Liberty.
Liberty is designed to meet the needs designed to be reliable, designed to be successful for the long haul.
I'm building Liberty, and I would definitely fly on it.
Liberty is the safest design, and I'd fly it in a heartbeat.
Liberty will provide the safest crew transportation to space.
I believe in Liberty.
Astrium is a proud member of the Liberty team. We are building Liberty.
I am building Liberty.
I believe in Liberty.
I am making Liberty safe and reliable.
Lockheed Martin is proud of our role in the Liberty spacecraft. We are excited to be building Liberty.
I would absolutely fly on Liberty.
My 4-year-old asked me if I could take him to the moon. I told him Mom is working on it. I am building Liberty.
I would take any opportunity I could to fly on Liberty.
My dream is to be an astronaut and fly on Liberty.
And hands off to the ATK team for putting that together, but at the end of the day, that's what it's all about, right? We're building a sustainable commercial capability to take that generation and the ones after. So, and with that, I think Mike's ready for questions.
So, yeah, did anybody come up with a real stumper for Mike? Because I'm telling you, he keeps telling me that he doesn't think you all can ask a question and then we'll stump him. A shirt, yeah.
You've only done a horizontal ground test with the 5-segment, right? So how do you know you've properly characterized the dynamic environment of flight to know whether or not the upper stage can take the loads?
Yeah, hey, great question. You're absolutely right. We've had 3 very successful ground test firings horizontal of our motor. Our engineers are feeling pretty good because it came in as predicted. You know, I'm a pilot, and I'm telling them, hey, well, you know, after having built 200 a little bit smaller versions of these, we should be that good. We are. We've done a lot of analysis to really answer your question with the second stage. And as John pointed out earlier, Ares 1 was really a system tuning problem. It turns out the natural frequencies of that second stage, that Boeing upper stage, absolutely fell right into line with the natural frequency of the entire system. So when our solid rocket motor, which has pressure oscillations of about 0.5 psi, actually less than a half a psi, the system tuned. It resonated, if you will. Because although dimensionally, our upper stage now from Astrium is 12 feet longer, 3 inches, within 3 inches of diameter, so it's very, very close physically. The fact that you've put the heavier tank on top, which is how you design a first stage, means that axial mode now has moved. We don't tune. So the analysis, and as a matter of fact, with NASA on technical interchange meetings, we've shown that to them. We can confidently say we don't have a problem. Now, if, as we mature the vehicle, if it drove back towards tuning or those modes, because we have control of the whole stack, we would stiffen that second stage, either structurally or with pressure, to make sure it didn't tune. But we actually feel very confident we do not need any mitigations. And the reality of it is that the tools are absolutely good enough these days that before we launch, we will understand how good that ride quality is. But we believe it absolutely meets NASA's requirements without any mitigation.
Reusable capsule. How many missions is it rated to be used for?
It's designed for 10.
10, and then you have to throw it away and build another one or re-engineer it or what?
So it would be just bring in another one. As far as if we evolve it into a little bit different or capability, we will see. You know, I've got an engineering degree, and I've been around a huge amount of engineers, and better is evil or good, right? So my philosophy is, hey, don't change a thing you don't have to. It introduces risk. And also, we're going to be instrumented so that we may, by the time we get to flights 8, 9, 10, be confident that, hey, the life is better than it was originally designed to.
Do you envision more than one up at a time, or only one mission at a time?
I think I need 4. I think I've got to have 4 to make the kind of operations we're looking at. So if you look at space station, 1 will be docked to station, 1 will be launching, so you'll have 2 at station at the same time, 1 showing up to replace the other one. And then in the turnaround process and then for contingencies, I really think kind of my minimum number for operating is 4, which allows me also to do a separate standalone mission with other customers.
It's pretty ambitious.
It is.
And then the second stage is reusable, right?
No.
It's not.
The second. As a matter of fact, that you bring that up, the first stage, although on the shuttle we reused it, we reloaded or refurbished it, that is not our plan. The business case tells us right now that we're better off just making it expendable. So, thanks.
Have you talked to insurance companies about how they'd feel with you downgrading the reliability for a satellite?
So we haven't talked to them about that. I have talked to insurance companies, and as a matter of fact, first flights, insurance on a first flight rocket can be fairly expensive.
Well, I guess my question is, does it really make sense if you got a production line going to actually reduce the reliability of a vehicle even though there's not people on it?
So probably in that sense, the reliability, probably not, because you can have payloads that are very expensive. We do have an independent system on board that's an evaluation detector, and it gives the crew insight and actually can initiate an abort. So if you have that system, we would pull off. So although it affects the safety of the crew for a payload, an expendable payload, it wouldn't make sense. So we would simplify the system some. And depending on how comfortable we are, we yes, could possibly pull off some of the redundancy in the avionics system. But your question is very valid. Is it worth it? The additional risk.
Can I ask you a question from Twitter?
Sure.
This is from Alan Boyle. He said, will you continue with Liberty if not funded in the next round?
Okay, so the question that came in via Twitter was, will we continue Liberty if we're not funded in this recent competition with NASA, with the Commercial Crew ICAP? And the answer to that is yes. We will continue. We have been, the past year, we have a Space Act agreement with NASA. It is unfunded. So all the development on Liberty has been on our own discretionary funds. We will continue along those lines. But the schedules we showed you here of where I'm flying crew in 2015, there's no way I can meet a schedule like that without an award from NASA.
Another question from the internet. They are wondering what the price range is for a flight.
So the price range, we are right in the middle of a competition in blackout, and that's a very fair question. Unfortunately, I'm not going to really answer it. What I can tell you is we are offering the service to NASA at a price that is less than what we're paying the Russians. And so it is